Hello everyone. So I'm recording this video right after the first one that I did for lab one. For this one, I'm gonna go over some of the concepts that you're gonna find in lab two. Now, I'm gonna start with the last part of lab two. I'm gonna show you the questions because the first part, I have a guide in there, in the canvas, where you can find the answers and you can also find the explanation for the Cartesian plane should be easy, you know, the area, the volume, elements, but the cylindrical and spherical especially, it might be a bit more challenging. So I have a guide in there, all right? What I wanna go over is the idea behind the gradient, divergence, and the curve. Because you see, you're going to be using those concepts in Maxwell's equations. For example, if we take a look at Gauss's law, you have that the divergence of the electric field is equal to the charge enclosed over E naught, which eventually you're gonna make it charge density. You can find this version of Maxwell's equation, where rho is a volumetric charge density. So this nabla, this is called a nabla, is a vector operator, right? And it's defined as the partial derivative with respect to x, I, plus the partial derivative with respect of y, j, plus the partial derivative with respect of z, k. And you can use this for vectors and scalars. For a vector, you find the divergence. For a scalar, you find the gradient. And then again, for a vector, you can find the curve. So Gauss's law can be written like this. Now you're gonna learn in the course, the first way you learn this is by the surface integral of the electric field. The area, let's put the area for now like that, is equal to the charge enclosed over E naught. And you're gonna learn that the surface integral can be rewritten as the divergence of the electric field. That's why you can get the rho, right? Because the derivative of the charge, so basically, and that's more the what you're gonna do in the course, the charge enclosed, you can find it for a insulator, especially, you can find it as the integral of the charge density differential of volume. So that's why you need a dV. In polar or spherical coordinates, that dV changes. Now, depending on the symmetry, it can be as dV equals to 4 pi r squared. Yeah. If it's a spherical symmetry. And that's what you're going to use a lot. All right. So let's show you how to do calculations using this nabla. All right. In X and Y and Z, it's not that bad. In cylindrical and spherical, there are some conversions that you have to apply, but that's why we focus more on the divergence, the curve, and the gradient in functions with respect to X, Y, and Z. All right. So I'm going to change some of those numbers given in the worksheet. And then I'll show you the individual questions. And then we should be good to go. All right. So what do we have here? It says, oh yeah, for example, here, divergence, right? What I was talking about. Given a, so let's say you are giving a scalar function in terms of X, Y, Z, given by, let's say, 5x squared y cubed. I'm changing it. I have to change it because there's no point for me to do the same. Plus 7 natural log of 2z. All right. So it's similar to what you have in there. So let's say I want to find that gradient, right? If you want to find that gradient, the gradient is always from a scalar function. So if I want to find the gradient of this, that's basically nabla phi. Now, this is in the worksheet, is the partial derivative respect of x of the function in the I plus the partial derivative of the function on j direction, that's the y direction, and of course, the partial derivative of the function in the z direction. So that's easy, right? So I'm gonna do that. Derivative of the function respect of x. Now this is z. So that what's the partial derivative of this respect of x? So it will be 0 for that. 5x squared. So if you do the partial derivative respect of x of 5x squared y cubed, you take the y as a constant, you just focus on x, that's 10x, so it will be 10x y cubed I. Again, if you take the partial derivative of a function just on z respect to x, there's no x in here. Okay, so we start with that plus the partial derivative of the whole thing in respect of y. So here, this is 0 because there's no y in there. We do the partial respect of y in of 5x squared y cubed. 5x squared is now constant. So I do the derivative respect of y cubed. That's 3y squared. 3 times 5, 15x squared y cubed on the j. And then on z, for z, there is no z here, but there is z here. Is 7 natural log of 2z. So you're gonna do the partial derivative respect of z of just this section, of just this part here. Natural log of 2z. Now, 7 is a constant, so I put it here. 7, the derivative of natural log is 1 over 2z. But wait a second, chain rule. The derivative of 2z times 2. So, look. So I have, oh, okay. And then you have 10x y cubed I plus 15x squared y cubed j plus 7 over z. Oh, sorry. Okay. Perfect. Consider, right? Now, in the worksheet, you have to evaluate. So let's say you have to evaluate for a point. So evaluate for a point. Let's say -1, 0, 3. So you just substitute 0, y, so 0, 0, y, 0. And then 7 over z, 7 over 3, so it will just be 7 over 3. Okay. That's my divergence of this whole thing. So very nice, right? It's a math exercise. Okay. If you're taking calculus 3, you should be, you have probably seen this or you want to see that. Okay. So here it is. All right. Let's now do the divergence. The divergence, you do it with a vector. So let's see what I have here. Evaluate the divergence. So let's give you a function that looks like that. I want to use log now, not natural log. As long as you guys keep it organized, you will be fine. It's all a matter of keeping it organized, all right? So let's give you a vector field equals to something similar. Let's say 3xy squared I plus 2z over y cubed j plus the log of, and let's just use the same, xy. Okay. So if you want to do the divergence of that, is just the nabla dot, it's like a dot product. Dot product, right? We just did that in the previous video. Delta over delta xi plus delta over delta j plus zk. So when you multiply, you're doing the i's with the I. So this will be this with just this. Because if I do I dot j, I dot j 0. Why? Because the angle between these two is 90 degrees. And if you remember, the dot product has a cosine of 90 zeros. Okay, that's one. So this will be respect to x of 3xy squared, and I dot I is 1, scalar. You want to get a scalar here. Respect of y now of just this. And then respect of z. All right, whatever. That's fine. Yeah. So respect to x, just like we did before, y squared is constant, so 3y squared. So the derivative respect of x is just 1 there, right? Respect of y, 2z, so 2z over y cubed, 2z comes out, the derivative respect of y of 1 over y cubed, guys, is just a fraction, right? So we write here 3y squared. The derivative of y to a power is the derivative of y to a negative 3. So that will be negative 6z y to the negative 4 or over y over 4. Right? It's just the derivative of 1 over y cubed. And there is no z here, so this is 0. It's just that. Now, if I have to evaluate in a given point, let's say point -1, 2, 3. So there's no x went away. 2 squared, 4 times 3, 12 minus 6 times 3, 18 divided by 2 to a 4, 16. So that's 9, 8, that's like 1 point, right? So 12 minus 9 divided by 8 is 1.1, let's say, something like that. So that will be 11 point or 10.9. 10.9. So that will be a scalar. Scalar, so simple. This is a cure. The cure is where you have to be careful. So I'm gonna give you the same function as before. We have the same one. Let's use a cure in a point given there. With a cure, you have to be careful though. Right. So Nabla cross V. And we just did cross product in the first lab. right? That's the first video for these tutorials. So this is equal to the determinant of I, J, K, respect to X, respect to Y, respect to Z, and then the X component here, which is this, the Y component, and the Z component. So it's just the same, but you have to be careful now because you're gonna copy, right? You're gonna copy these two columns. So I'll do it here. I and then this and this column here. There you are. So okay. So look what we find, right? Derivative respect to X of this, but there's no X here. There's no X. So that will cancel. There's no J, there's no K component, zero in that. Respect to Z, there's nothing. Okay. And look at this. So there's no C, so cancels. Now here we have, in this one here, this diagonal, we have the derivative respect of Y of the log X, Y, there, in the I. So how do you find the derivative of the log? Look, remember that log of xy, you can say is natural log of xy over natural log of 10. That's what we call change of base. And I want to do that here because it might be easier for you guys to see the derivative log 10 comes out. The derivative of natural log of xy respect of y, it will be 1 over xi, xy, and then the derivative respect of y of xy, which is x. Nice, right? A bit more of work. X cancels, so it will just be 1 over natural log of 10 multiplied by y in the I direction. That's all it is. Be careful. All right, let's. All right, but we haven't finished yet. Now let's erase that one on the top. We don't need this anymore. Let's go here. So here, look at this. J I. Okay, this one, they all have it. So respect to x of log of xy. So it's going to be the same, but now respect to x. So the derivative respect to x, now in the j of log, it will be, if I follow the same pattern, 1 over natural log of 10. Now instead of y, it will be x. All right. 1 over xy. Yeah, 1 over x. So j. Right, there you are. That's in the j. Now this one, respect of z of this I. So the derivative respect of z of 2z over y cubed is just 2 over y cubed, easy, in the I direction. and then the derivative with respect of y, 3xy squared is 6xy in the k direction. So it's gonna be a bit long in there. Let's move this so I can show you the answer. The bottom minus the top. So 1 over y ln 10 I minus 2 over y cubed I minus 1 over x ln 10 j. So that's the I, the j, and the k minus 6x y. Okay. Can sort of see that, right? Let's bring this closer. See there. All right. Now let's evaluate on a point. What point do they give you here? Negative 2, 3, and 10. Let's make it negative 1, 2, 1, 5. So let's make it a point. Negative 1, 2, and 5. So for x negative 1, y 2, so 1 over 2 ln 10 minus 2 over 2 cubed, 2 over 8. That's all in the I. Minus 1 over minus 1 plus 1 over natural log of 10 j minus 6xy plus 12. Okay. There you are. All right. That's how you do cube. So mathematical, the first two labs, guys, as I said, it correlates with what you're going to be doing on the first week or even 2 weeks of classes. All right, so that's basically what you have to do here. All right. And then you're just going to the, well, then you have to define closed curves and closed surfaces. If you check Gauss's law, for example, I'll show you this. Gauss's law uses an enclosed surface. We call it a Gaussian surface. Here it is. For the closed path, yeah, closed curve. Closed surface is that. Closed curve is basically your closed path. That's Ampere's law. Ampere's law uses a closed curve. Yeah, there. This is a path of the magnetic field. You will learn that also in this course. Here, let me see that. That's not difficult. All right. Now for the first questions, guys, this one, part 3, 2, and 1. Use this. This is it's gonna be in the Canvas, and here they explain you the x's, y's, right? For example, this makes sense. Your differential of length. You've seen that in Physics 1. The area, the x dy, the I z, the x z, depending on which one you are taking. Top, like in a square or in a cube, you can take the top face, the lateral face, or the ones on the sides, right? That's your x, y, and z here. Yeah, simple. And then the volume is just that. So that's simple, right? For cylindrical, you just have to be careful because now you have the circle and then you wanna have the z, right? But the z is just z. The x and y plane, because you have circles, you're gonna define an angle phi. Now, I remember when I used to teach, or when I teach 201 in class, right, the lecture, some students get confused because that angle in math they define it as theta. right? The angle on the X and Y plane. So just be careful because depending on the textbook, they can use phi, it's the same. And at the end of the day, that angle goes from 0 to 360. All right. So if you have your Z, if you have your Z axis, your Y and your X axis, or your X and Y axis, right? You're gonna define a circle here. So you can define a circle with radius, and they call it radius rho, and this is the angle theta or angle phi. So then if you break into components, if this is your X, this is your Y, this angle will be, this will be the, if you do the projections like you do in the X and Y coordinate, the X will be rho cosine, and the Y is your rho sine. You're just doing the projections in the, like within the Cartesian coordinate, but now you're doing, remember, this is X and that's Y, right? And Z is just Z here. Z. That's why you have rho phi Z. And this is the same that you see in polar coordinates. All right? So that's how you convert X, Y into rho, phi, and then Z is just Z. All right? And this allows you to find area elements and volume elements. The area element, for example, if you're looking at an infinitesimal division, look at it here, like here, right? This is the phi. So this is rho the phi. And if you're looking at something here, right, that you can find one differential of area equals to rho the phi the rho. That's here. But then remember, we have cylinder, and I want to show you the on the slides. You can have a cylinder here. So you can also have an area element on the lateral view, right? So in that one, you will have the rho the phi. All right. Oh, that was the one here, right? But if you have it on the top, you start having the dz element, right? Times rho the phi, for example. And that's also in the cylindrical coordinates. Let's actually show you that in here. That's for the area elements, right? What I show you is, well, this, show you this, and then the Pythagorean theorem still works, but the area elements are here. So this is the one I was showing, right? The rho the phi. There you are. There. Right? But you can also have the rho the phi the z. That's the one. It's a bit harder to draw that in the whiteboard, right? But you can see this one is the one I drew here. And then if you elevate, like you can sort of do it here, right? There, that's the z. So rho the phi the z. It's another area element. And they ask you those questions in the lab. Oh, there it is. And then for the volume element, and this is the one that we have here, yep. For the volume element, it's just rho the phi the rho the z. It's just that. All right. So it's the infinitesimal volume element. So that is what you can find in this guide that will help you to answer the questions. Well, the part 1 Cartesian, part 2 cylindrical, and then for part 3 spherical is the same. You just have to follow what you find here in this guide for spherical coordinates. It's just r theta phi. Okay, not r theta z. So now you have a phi element in there. And then for the submissions, you're gonna have that activated. And you're gonna have this. So the individual questions You're gonna do a divergence like we did. You're gonna do a gradient, a curl, and you're gonna show using a spherical coordinates. This, look guys, to show that, all right, to show the volume of a sphere, I'm gonna give you the integration here. It's a triple integral. Right? You can do it in spherical, in fact, that's in spherical coordinates. Because you have the r theta phi. So you're gonna integrate dv in spherical coordinates. And you're gonna find that the vector r is the main one. Integral of r is what is a volumetric element, by the way, of the doing thinking in cylindricals. Yeah, so pretty much r goes from 0 to r. D theta in the spherical coordinates, theta in the spherical coordinates goes from 0 to 180. Is the angle with respect to the z, to the what will be the z axis. So, and phi is the angle that was on the ground. So oh, I forgot. There's a sign value there, right? Yeah, my bad. So r dr, that's your RQ, r free over free. Sine theta, you have to integrate it. The integration of sine is minus cosine, don't forget. You evaluate from 0 to 2 pi, that will give you 2, think about it. And d phi from 0 to 2 pi, that's 2 pi. And you will get you 4 over 3 pi r cubed. It's very easy. So that's it for this second lab. It's not that much. It's a continuation of lab 1 if you think about it. I will do only online office hours if you have any questions, but this, what we did before, should be covered in the lecture. The next week lab is when we start experiments on electric fields and then later on circuits and capacitors. All right. So have a nice rest of your day. I'll see you guys on the next video.